Now there will be third lecture by Dr. Bakshi on fundamentals of surface active species. Now invite Dr. Bakshi.
Good morning. With the third lecture, and this is devoted to the fundamentals of species. Here we will talk about the definition of the surface active species, what problems species absorb at the interface. Mainly, we will be talking about the surfactants and their interfacial properties. Why we need to understand the fundamentals of surface active species? As we mentioned last time, without the surface active molecules or the amphiphilic molecules, we cannot produce the stable colloidal suspension. I mean to say that when we have to produce a nanoparticle, and in the aqueous phase, if this is the nanoparticle, we need to create a bilayer around the nanoparticle, and this bilayer around the nanoparticle is created by the surface active molecules. So how the surface active molecules are going to occur, that is the colloidal properties and hence produce the stable suspension is being used for different kinds of applications. What is the meaning of a surface? Suppose if somebody asks you in terminology, this surface is interface between the solid substance and that of the gaseous environment. So exactly the same way, wherever there is interface, no the surface. So here, so we can say, but in fact, this is the interface between the immiscible phases. The molecules of the air, they do not want to mix with the molecules of water because of their entirely different properties. Molecules of water, they are polar, whereas molecules of air, they are non-polar. Hence, practically, there is negligible miscibility among the molecules. Surface active molecules, they have the ability to simultaneously interact with both phases, the polar phases as well as the non-polar phases. The polar phases, towards the polar phase, the surface active molecule includes its polar functional group, whereas in the non-polar phase, the non-polar functional groups are embedded in the non-polar phase. Therefore, a single molecule possesses dual ability to simultaneously interact with the two miscible phases. This is because that molecule is possessing polar functional group as well as non-polar functional group. How we can generate such kind of molecule? If you simply look at this molecule, and if you ignore it, there are three methyl groups. And if I replace this hydrocarbon chain with the methyl group, this is uh, ammonium, alkyl ammonium substituted ammonium ion. If I am going to remove one alkyl group with the hydrocarbon chain, it means that the non-polarity that was incorporated by the methyl group has been enhanced by the number of methylene groups. So therefore, this functional group possesses predominantly non-polar character, whereas the head group possesses predominantly polar group. So therefore, overall the molecule, basically it is the ion. If you ignore the bromide, and this cation possesses two functional groups. The one is the polar functional group, the other one is the non-polar functional group. Such kind of molecules cannot entirely solubilize the aqueous phase, either they can be solubilized in the in the non-polar phase because of the polarity they are possessing. So therefore, these molecules are forced to be accommodated only at the interface. So the part of the functional group that is polar in its properties, that is going to interact with the polar phase, whereas the non-polar part, that is the non-polar functional groups, that is going to interact with the non-polar region of the other phase. So these molecules, for the non-polar part is known as hydrophobic. It has no ability to interact with water, but it has kind of a phobia of water. It runs away from the phase, whereas the hydrophilic group, it is polar and hence it has the ability to interact with the water molecules. This dual ability of a molecules possessing the non-polar and the polar functional group, or possessing the hydrophobic and as well as the hydrophilic functional group in the same molecule, they are known as amphipathic structures. Now, such molecules, they are required in order to create a stable colloidal suspension, because if they are going to arrange at the air water interface, because that is much easier for us to understand, so they can also arrange themselves at the solid liquid interface. So therefore, if the molecules are going to be arranged at this interface, suppose if you ask me how many interfaces you could see over here, the one is over here, that is between air and fluid phase. Other one is over here, that is between solid and the fluid phase. Another one is over here, solid and the gaseous phase. So the molecules, because these molecules, they reside in the fluid phase, so therefore they occupy all the interfaces. It's not only the air fluid interface, but they also occupy the solid fluid phase. That solid fluid phase here, our main objective is to understand that how the molecules, they are going to absorb at the nanoparticle interface, that the solid fluid interface. How we can synthesize them? The most prominent example for the synthesis of the amphiphilic molecule is the saponification. It's the soap making chemical reaction, and it's the esterification. You know that we can take the ethyl stearate over here and we treat with the sodium hydroxide, and this way we can create the soap. It's the salt here, the sodium stearate. We create the sodium stearate. Now, this soap, you know very well that it has the amphiphilic property, exactly the way we are showing over here. The only difference, it's the same kind of a molecule. So here we are dealing with the anion that has the amphiphilic properties, because here the cation is not a surface active ion, but the anion is the surface active ion. Here it is the cation and the surface active ion. Now this anion, which is the surface active ion, so it has the ability to interact or to absorb at all the interfaces. For the sake of clarity that how this anion acts as soap, we only show, suppose if we have the suspension of oil, that could be in the aqueous phase, or the oil could be on your any kind of clothes, and when you are going to immerse the clothes in the soap solution, what happens? You may see this oil may be on the surface of the clothes, or it is embedded in the aqueous solution. So as soon as you are going to add the soap, this oil is non-polar molecule or the non-polar phase. The non-polar functional group of the amphiphilic molecule, so that is going to be embedded in the non-polar oil, whereas the polar function groups, they will remain in the aqueous phase. Now you could see that by inserting the tails into the oil, it increases the solubility of the oil in the amphiphilic molecules aggregated state. So these molecules, they aggregate or arrange at the interface that is oil aqueous interface, and hence they pull the molecule from the solid surface and they dissolve them into their aggregate. So this is the aggregate of the amphiphilic molecule, and the solubilization of the oil is only happening, or it is only driven by the hydrocarbon tails of the hydrocarbon chains of the amphiphilic molecule, and this way the oil particles which are sticking to the surface of the clothes, so they are being picked up by the soap solution. So this mechanism is always working during the washing process of the dirty clothes in the presence of soap. Now, the most important thing over here, you have seen the aggregation of the molecules in the form of a spherical shape. What forms the aggregation of molecule in the spherical shape? Or in other words, somebody asked you, I can understand that the stability of the colloid is important because you need the bilayer in order to stabilize it, so that this particle should not interact with another particle like this, and the particles remain suspended in the aqueous solution to make a colloidal suspension, that is a stable colloidal phase. But the problem is, what concentration we should take? Is there any kind of judgment or the estimation that which concentration is required so that we can completely coat the particle? So now that is the most important aspect here. If you have the required amount of the concentration that is less than the ability to provide the bilayer, the colloidal particle is not going to be stabilized. So therefore, the concentration of the amphiphilic molecules must be much greater than the concentrations required of the particle. But how we can judge that? We need to use for the layer around the nanoparticle, and that is related to the behavior of the amphiphilic molecules to aggregate in the kind of spherical. What are the different kinds of molecules? See here. So it means that the surface ion for a molecule could be predominantly negatively charged or positively charged, or it could be neutral as well, but it has the ability to interact with the phase or the aqueous phase. On the basis of that, the surface active molecules are divided in different categories. That is, here the head group is positively charged. You see the ammonium, phosphonium, again ammonium, right? So these are we have changed the length of the hydrocarbon. This is tetradecyl C14. This is also tetradecyl C14. This one is hexadecyl. It is C16. So C16 hydrocarbon chain length. I mean to say, somebody asked you that what is the meaning of that? The end of this line represents the methyl group CH3. Here it is CH2. So I can just let you know how to count the length of the amphiphilic molecules. So it is CH3, CH2, 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 CH2. How many? 1, 2, 3, 4, 5, 6. And if I keep on going, CH2, CH2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And so you need 3, 4, 5, 6, 7, 8, 9, 10, 11. And here you have the last one, CH2, and then that is connected to ammonium group. So it could be CH3, CH3, and CH3. So you can see 1, 2, 3. The 1 starts from this side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it is C12 hydrocarbon chain. So C12 is do-decyl. So do-decyl hydrocarbon chain, and in this way you could have do-decyl, and likewise you have tetradecyl and hexadecyl. So the meaning for tetra is, so there are C14 and C16 methylene groups, so those are present in the hydrocarbon chain. Right. On the basis of that, it is the nomenclature we use for the surface active molecules. The rest nomenclature, where we have to know about that what kind of ion or cation is, that is related to the presence of particular element, which is having the quaternary structure. Here you see the nitrogen, ammonium, and here it is the bromine. And then you see the phenyl group, and here they are the methyl group. So these terminal groups could be anything. So most of the time they are identical, or they could be non-identical or different function groups as well. So you see now, if I'm going to increase the chain, by increasing the chain, what I'm going to do, I am increasing the known polarity. So known polarity increases as the length increases from C12, C14, C16, and so on. By increasing the known polarity, I am increasing the known polar, the ability of the functional group to interact with the known polar phase. So known polar, a known polar ability of the functional group that increases, or you can say the water wall interaction with the HEPA, which it can interact with the other known polar phases, so that increases. And here you could see different kinds of surface active molecule. This one is, when you have to identify the surface active molecule, you must keep your attention on the charge of the head group. So this is known as a head group, right? So you can say that, I mean to say that you can depict the surface active molecule, the surfactant, in the form of a tail. If I'm showing the tail over here, and the polar part is the head. So this is the polar part, you see. So it is the tail and head. So tail is non-polar and the head is polar. So it is identical to the molecular structure of the molecule. So usually when the surface active molecule is depicted in this schematic form, so it is automatically demonstrating that the tail part belongs to the hydrocarbon chain length and the head group belongs to the polar part. So on the basis of the head group, you can divide the molecule into different categories. If the head group is positively charged, it's called cationic surfactant, negatively charged anionic surfactant. When the head group is possessing no net charge, but it has the ability to interact with atmospheres, we call it the non-ionic surfactant. And when the head group is possessing the dipole, means it has the positive net charge as well as the negative net charge, so then we call the zwitterionic surfactant. So you can choose any one depending upon the fact, or most of the time for the colloidal stability of the gold nanoparticle or the transition metal nanoparticle, that could be the gold, silver or platinum. So it is better to use the ionic surfactant. You may use the cationic or the anionic surfactant, and they provide much better colloidal stability because the adsorption, I think I'll show you over here. Okay. So the adsorption on the surface, suppose if I say that this is the surface of the particle. This is the surface of the particle, nanoparticle. I'm simply writing NP. Right. So then how the surfactant is going to adsorb? It is going to adsorb like this. Right. The head group is going to be going to be adsorbed on the surface rather than the tail. Now, if somebody asks you that what prompts the head group to adsorb on the surface of the nanoparticle, you'll be saying the transition metal nanoparticle, like gold nanoparticle, they have the free electron cloud that is mobile, and hence the surface is charged. So therefore the charged surface is going to interact with the charged head group rather than the tail. So usually the tails are not going to adsorb on the surface of the molecule, it is the head group. And since the tail cannot stay in the aqueous phase, so therefore another molecule is going to, another layer of the molecule is going to be arranged in the inverted direction, so that the tails are going to interact with the tail, and these head groups are going to interact with the water molecule. So therefore, now this is solid liquid interface. Solid liquid interface. Now the solid liquid interface, exactly the way the air-water interface is being occupied by the surfactant molecule. So here in the case of the nanoparticle, this is the solid liquid interface that is going to be possessed or occupied by the surface active molecules. If you need a stronger adsorption, much stronger adsorption, then you could see that this is the single tail, right? If I remove another methyl group, suppose if I am going to remove another methyl group over here, I can introduce another tail, another hydrocarbon chain, just like that of the previous one. So here I have another hydrocarbon chain. You see, one is over here. This is the first hydrocarbon chain, and this is the second hydrocarbon chain connected to the same head group, right? Or we can have the two head groups. Suppose if I say that there is, let me remove this, just a minute. If I alter this, so I have two ammonium groups, okay? So now I have two ammonium groups, CH3, right? And I have two ammonium groups, you see. So it means that you may say that it is the double head group. Yes, if the length of the spacer is long, so we can say it's double head groups, right? And the double head groups, one head group is connected to one tail, another head group is connected to another tail. Such kind of molecules are known as Gemini molecules. You see over here the difference. The diagram, the sketch here, what I am showing, by replacing one methyl group with the second hydrocarbon chain. And so by doing so, there is one possibility that I could keep just one ammonium functional group and two tails, or I can have two ammonium functional group. One is separately connected to one hydrocarbon, another one is connected to another hydrocarbon chain. So here is the comparison. When you have the one hydrocarbon chain, we call it monomeric. When you have the double hydrocarbon chain, we call them the dimeric. So see over here, this is one hydrocarbon chain. It is C12. You can have identical C12 here, C12 and C12. And you see there are two head groups. The one ammonium functional group, another one ammonium functional group, and they are separated from each other through a spacer. We call this a spacer. The spacer could have any length. It could be of just one methylene group, 2, 3, 4, 5, any spacer length you can introduce over here. You can increase the spacer length, right? But you have to keep in your mind that you are putting more methylene groups in spacer. Obviously, you are reducing the polar ability, the polar ability of the polar functional group by placing the non-polar, because methylene groups are non-polar. CH2 over here. So by putting the non-polar functional group, in fact you are reducing the ability of the head group to interact other polar phases, because there is the non-polar functional group that is inserted in the head group region. So such kind of a molecule is known as Gemini commonly as Gemini because there are hence we call them a Gemini molecule. So Dodecyl is the length, trimethyl ammonium bromide and likewise hexadecyl trimethyl ammonium bromide. But here you might be remembering the nomenclature. So when we have the two identical functional groups, so we use bis. So dimethylene means it is the spacer, it is referring to the spacer. Di means there are two methylene functional groups connecting to bis. This means the two identical, you see the two identical decyl dimethyl. Decyl refers to C10. Dimethyl, so dimethyl are the methyl function group on the positive charged nitrogen. So dimethyl ammonium bromide. So it is bis. It means that there are two functional groups exactly of the same molecular structure. So that is why we are using bis. Likewise over here you can see again dimethylene. Again there are two methylene groups. Those are creating the spacer. And we have dodecyl bis, dodecyl dimethyl ammonium bromide. So in this way we have the nomenclature. We use the name IUPAC name for naming the acrylic molecule, the surface active molecules. Now how we can determine by simple experiments that they are really surface active? Obviously, if we need to understand they are surface active, the most important property is the interfacial tension. So the surface tension of the water in the absence of the surface active molecules is close to 61 or 62 millinewton per meter. So and when we start adding the surfactant or the amphiphilic molecules in pure water, the molecules, they first go over here in the atmosphere, but they prefer to absorb at that interface, thereby they reduce the interfacial tension. So you see interfacial tension is represented with the electrostatic drama. So as we increase the concentration of the surfactant, interfacial tension reduces. Eventually a point comes. After that, if you keep on increasing the concentration, then the surface tension becomes constant. The meaning of that is the interface is completely occupied, but whatsoever the surfactant or the surface active molecule you are still adding into the solution, they are going in the aqueous phase in the form of aggregates. These aggregates are known as micelles. In surface active or the surfactant chemistry, the aggregates of the molecule, those are being produced, we call them the micelles. And this one, the surface tension was the interfacial property, but likewise you need to know that what is the evidence for the micelle formation in the bulk. The bulk is the, in order to evaluate the bulk property, you perform the conductivity. If you are dealing with the ion surfactant, so the conductivity is the most convenient technique which you can measure. Every college or high school, so they have the conductometric instrument. So first, in pure water, the pure water which is DRS water, the conductivity should be close to 0. It is usually in the 10 to the power minus 6 range. But when you start adding the surfactant, conductivity starts increasing because you are creating ions. So these are the ions when you start adding the surfactant, and hence the electric current carrying ability in the water phase is by the ion. More and more ions are going to have the greater ability to carry the electric current, and hence the electric conductivity that increases. Eventually a point comes at a high concentration where you see a break. You see a high concentration, the high conductivity with a greater slope, and this portion is with the lower slope, smaller slope. It means the connectivity of this region, those species which were contributing towards the connectivity in this region, they were having the higher mobility to carry the electron density or the electric current. On the other hand, the species which are produced in this region, they are not carrying that much amount of electricity as much was being carried over here. So therefore, obviously, there is certainly a change in the solution property or the change in the species those have been created. So those you could see over here. When you have the single molecules, the single ions, those are present in the solution, obviously they have the greater dynamic mobility in the solution in comparison to the aggregated state, aggregated phase. So the aggregated spherical phase of the amphiphilic molecule, it faces greater viscous drag in comparison to that of the non-aggregated phase. So therefore, this aggregated phase, because it is also polar, carrying the positive charge if the surfactant is positively charged, negative charge if the surfactant is negatively charged. Right. They can also carry the electric current, but their mobility in the aqueous phase is obviously much smaller in comparison to that of the monomeric phase of the molecules. So hence, the connectivity, the slope is less in comparison to the slope in the region before that. So this is, I mean to say that these two studies complementary explain the creation of or the formation of the micelles. The most important thing over here is that we are going to talk about that how these micelles are required when we have to talk about the colloidal stability of the nanopart. How the micelle formation in the aqueous phase is the key to determine the stability of the nanoparticle in the aqueous phase. First, I'll take you to explain that what kind of micelles we are going to talk about. You see over here, molecules arranged in a sphere. But if we have a different kind of molecules, right, both are amphiphilic. You see the red and the blue? Both are amphiphilic molecules, but they have the different functional group. So they could be cationic, anionic, or they could be cationic, zwitterionic, they could be anionic, zwitterionic, cationic, non-anionic surfactant, anionic, non-anionic surfactant, any kind of combination we talk about over here. So having the different kind of combination, we call them the mixed micelle. This aggregate is known as micelle. So when it is of the single kind of a molecule, we call a simply micelle. But if the different kind of molecules are involved to create the micelle, we call it mixed micelle. And this is the example for the ionic and ionic, and this one is for the non-ionic and ionic. This one is non-ionic, though it has the head group as well, but it's not the polar head group the way we are showing for the ionic surfactant. So this is the mixed micelle for the combination of non-ionic and the ionic surfactant. What is the anatomy of a micelle? This is the anatomy of a micelle. I'm showing it in a much broader picture. You see over here, I am talking about the same micelle. If somebody asks you, I can understand that the aggregates are formed. But I'm still confused that where is the polar part, where is the non-polar part, how the polar part is differentiated from the non-polar part, or what are the properties of the aggregate of the micelles as far as means in terms of the micelle water interface. So all those things, all those questions we can reply if we know the anatomy of the micelles correctly. So first, I want that you simply focus your attention on the micelles. So I've divided the micelle into different regions. This is the interfacial region. This interfacial region is known as stern layer. You see over here? Stern layer. We call it stern. The word stern is related to the scientist who explained this. So this stern layer is occupied by the head group, the polar head groups. Now you might be saying that if this is positive charge, this is positive charge, how they can reside close to one another in the stern layer or in the stern region, because they are having the identical charges, because identical charges, we know, they repel one another. So therefore, identical charges are balanced by the counter ion. You see, this counter ion is oppositely charged. What is the meaning of this counter ion? This is the same bromide ion here we are talking about. Here, this bromide ion. Head group is this. So one head group arranged in the stern layer, another head group is arranged. This bromide ion is taking the space among them, so that this should not repel this another identical polar function. This oppositely charge is going to take the position over here. That is the thing which we have explained here. So all these white balls, white circles, you could see, so they are the counter ions. They could be bromide, chloride, or iodide. Now this stern layer is the polar region, and it means that the surface of the micelle, it's a kind of, suppose if you have to visualize that how the aggregate, or in 3 dimension, how can we visualize the micelle in 3 dimension? I'll say that simply you could see that it's a ball. It's a 3-dimensional ball. The surface of the ball is lined with the stern layer, and it is the polar, because it constitutes the polar function group, the polar head group, and the counter ions, and hence it is interacting with the water. So here it is the pure water molecules. So therefore the polar region of the micelle is in contact with the water atmospheres, and this is core. So core is entirely non-polar, because you see, as you move away from the head group towards the end, the non-polarity increases. So the first 2 methylene function group, those are connected to the ammonium head group. So they are still under the influence of the positive charge. But as you move away and away, the ability or the influence of the polar head group, that reduces, and hence you are entirely in the non-polar region. So that is why this is entirely a non-polar region. So contrastingly, the center is entirely non-polar, the surface is entirely polar. So therefore you can divide another 2. Now the second region is outer palisade layer. The outer palisade layer is predominantly influenced by the head groups. You see, this methylene group, this methylene group, this methylene group. So it means the first 2 methylene groups are completely influenced by the polar head group. So therefore they are still possessing certain amount of polarity, because they have the influence under the head groups. But when you are going over here, so then the effect of polarity is reduced dramatically. So this is the inner palisade layer, the palisade layer, or the inner palisade layer, and this part is predominantly now non-polar, and this part is entirely non-polar. So in this way we divide the micelle into different portions, and I'm going to explain that what is the meaning for that, why we need to divide it, because micelle itself is a kind of a pot or a reaction vessel which has the ability to dissolve any kind of a molecule, no matter which polarity it is possessing. It has the ability to dissolve the polar component, because we have the outside the stern layer, that is polar. It has entirely a non-polar core, so therefore any hydrocarbon molecule which will otherwise be not solubilized in the pure aqueous. If you are going to put a drop of oil, you cannot solubilize, but if you put the drop of oil in a micellar solution, you can dissolve that. So that drop of oil is going to be accommodated in the core of the micelles. Mathematically, how can we quantitatively determine the characteristic properties of the micelle? The first one is the aggregation number. Aggregation number means how many monomeric molecules are arranged in a sphere to create a micelle. That is the aggregation number of the micelle. Radius of the micelle. You see, the radius of the micelle is, we have to start from the center all the way going to the surface. So it means that it is, I have not shown the end of the tail, but basically these tails are going to be extended exactly up to that. Suppose if you ask me, is it empty or the vacuum over here? I'll say no. This part is entirely non-polar and it is occupied by the end of the tail. So therefore, the radius of the micelle is extending from here to here. Entire is the diameter. So it means that if you have to calculate the radius, obviously you need to know the length of the hydrocarbon tail plus the concentric area of the stern layer. So that is the radius of the stern layer, and that is the radius of the micelle. Volume of the micelle, because it is sphere. If you know the radius, it's 4 by 3 pi r cube. So radius, you know the radius and you can calculate the volume of the micelle. Suppose if you ask me, what is the conventional surfactant like sodium sulfate? What is the volume? I'll say it is very tiny, right? And maybe close to just few nanometer, right? 1 or 2 or even less than nanometer, depending upon the tail length, right? And volume of the core. So you can also calculate the volume of the core, but the volume of the non-polar region, hydrophobic part. H stands for the non-polar or hydrophobic part. That is core as well as the palisade layer. So if you are having up to here and here, that is usually we include the outer palisade layer as well, right? So the non-polar portion extends from here to here. Predominantly these the first and the second methylene group, they are more under the influence of the polar region rather than the non-polar. But still we can calculate the volume of the non-polar, or the hydrophobic region. Again, we can choose the L. So L is the length of the hydrocarbon tail, excluding the stern layer. So it means that I am simply talking about the length of the hydrocarbon, excluding this portion. From here to here, that is referring to the volume of the hydrophobic part of the micelle. Volume of the stern layer, so you know the volume of the micelle, the entire volume of the micelle subtracted by, and we can subtract the volume of the hydrophobic portion from the entire volume of the micelle, that will give you the volume of the stern layer. Volume of the tail, you can calculate, this is the mathematical formulation. You can calculate the volume of the tail, that is 27.4. You don't need to go through the mathematical formulation. 27.4 plus 26.9 multiplied by N stands for the number of hydrocarbon chains, and C the methylene groups minus 1. So you can also theoretically calculate the aggregation number. N stands for aggregation number, that is volume of the hydrophobic portion divided by the volume of the tail, and that would also give you the aggregation number. I mean to say that if you have the entire volume, and if you are going to divide the entire volume with only the volume of one tail, you will be able to calculate the aggregation number. How many tails are there in fact? Length of the tail 1.5 plus 1.26 multiplied by N. So as many methylene groups are there, so in this way you can calculate the length of the tail. So I mean to say that these are the characteristic properties of the micelle. Okay, so just a minute, let me see how many. Okay, yeah. So now somebody can ask you, are we expecting the micelles always existing in the spherical shape? No, that is not. But the initial aggregation, when we increase the concentration of the surface active molecule, that takes place in the aggregated or spherical state. If we keep on increasing the concentration, we transform the shape from the sphere to the cylindrical micelle, and then if we keep on further increase the concentration, it becomes a plate-like micelle. So I'll show the images for that. So here is the definitions for the different parts. So this is the head group surface area. We call the surface area S. This is the volume, overall volume, and this is the length of the hydrocarbon portion. So surface area we know 4 pi L square. We have already defined L in the previous, and the volume is 4 by 3 L cube, and hence we can say N multiplied by the volume. Here we are talking about the volume of a single molecule, or the hydrocarbon chain for the molecule. So if we divide V by Ls, so it is 1 by 3. So this is the surface area for that of the spherical micelle. Likewise, this is 1 by 2 for the cylindrical, and it's 1 for that of the plate-like micelles. These are the theoretical considerations. Somebody can ask you, can you show me actually in an image where are the spherical micelles? Is there any way to see them in an actual image? Yes, we can see them in the actual image. But first I'm going to tell you that how this transformation happens. We first deal in the aqueous solution when the concentration is very low. The molecules exist in a single species, that is the monomeric form. We call them monomers. By increasing concentration, we convert them to aggregate spheres. Further increasing them, it's a rod or thread-like structure. Further increasing them, we produce the vesicles. The vesicles are the same which we talk about in biology. And you could see over here, in this case, this entire transformation is happening in the aqueous phase. The aqueous phase is over here, and the head groups are in contact with the aqueous phase. What if we talk about in a non-aqueous phase? It means that in non-aqueous phase, the tails have to be oriented towards the non-aqueous phase. What kind of non-aqueous phase? Somebody can ask you. What if we replace water with hexane? Are we still expecting the same kind of aggregates? We can expect the same kind of aggregate, but then the shape is inverted. You see, this is the reverse. Here the head groups are towards the aqueous phase. So when I'm going to replace the aqueous phase with the hexane, then the head groups cannot interact with the hexane, and then the shape is inverted. Then the tails they are hydrocarbon non-polar, they are going to interact with the hexane. So that's why we call them the reverse micelles. Reverse micelle. And so the same is the story for the lamellar structure here. As you see in the rod-like, thread-like micelle, head groups are in contact with water, and here, if hexane, the tails are in contact with water. So this is the way transformation helps. You need all this information. Why we are going through this aspect, which has a little relevance to the nanoparticle synthesis, but that is not the thing. When you have to properly produce the stable nanoparticle suspension, you need the knowledge of everything. Only then you can generate the stable suspension. Okay, here is the transmission electron microscopic image. You see the dots, black dots? These black dots are in fact the micelles. And what are the dimensions? This is 100 nanometer. And you could see that if I have to split the scale bar to here, half, this is the 50 nanometer, further half 25, further half close to 12 nanometer, further half 6 nanometer, 3 and close to 1. So practically the size of the micelle is close to 1 or 2 nanometer only, right? So these dark dots, they show the nanometer. What are the elongated micelles? Thread-like micelles, which I was talking about over here. Yes, when the micelles, they merge with one another, they produce the thread. You see the thread over here? Thread. So if we keep on increasing the concentration, more threads and longer threads are generated. You see the threads over here? So they are the longer thread. It means that more and more micelles are going to fuse with one another to produce the longer threads, right? And if I further keep on increasing, then at some point the bilayers are produced, and eventually those bilayers are converting. I mean to say that it is basically the threads are now in much elongated state. So here you may not be able to see the bilayers, but they are now, they have produced the bilayers. Since the threads in fact are the bilayers, and now eventually the bilayers are going to merge, or the threads are going to, threads, if I have a thread, and if I connect the end of the thread, or merge the thread, I can produce a circle, that is vesicle. So I mean to say that the vesicle, what is vesicle here? If I have a thread, longer thread, and if I join the ends of the thread, I can make a circle. But inside there is water pool. Inside there is water pool. This is known as vesicle. Where are they? All these circles are vesicle. You see, vesicle, vesicle, vesicle. Now you see the dimensions are increasing simultaneously. Scale is the same, 100 nanometer, 100 nanometer. But now here the dimension, if I have to see that what is the dimension of this one, obviously it is somewhere over here. If this one is 50 nanometer, it's close to 25 nanometer. So it means the vesicle structure, the diameter of the vesicle is close to 25 nanometer. So in this way, the size increases. So I must conclude this, that why we need it, because before I stop this, I just want to explain in 1 or 2 minutes that why we need these micellar properties. The first thing is that because our main objective is to create the stability of colloidal particle. Let me have a colloidal particle. This is a colloidal particle. Okay. So it could be a gold particle, you may say a silver particle, or anything like that. So surfactant is going to adsorb at the surface. The head groups are arranged like this, and the water molecules are here. So they are all water molecules. Tails cannot stay in water, so therefore there is another layer. This is the bilayer. You see, this bilayer, I can say it is the bilayer that is coating the nanoparticle. This is nanoparticle, gold nanoparticle, you will see, right? And this coating or the bilayer, which is coating the surface of the nanoparticle, is providing the colloidal stability. The bottom line is that what should be the concentration? In order to establish the bilayer, what should be the concentration? We, the whole fundamentals of the surfactant chemistry I have explained over here, just to arrive at that what concentration we should choose. We should choose the concentration of the surfactant which is much higher than the concentration where the micelles are formed. What is that concentration? So as you see that in connectivity experiment, this is the concentration, we call it critical micelle concentration, where micelles are produced. It means that if I have to stabilize the nanoparticle, the concentration of the critical micelle concentration of SDS, CMC of sodium dodecyl sulfate is 8 millimolar. Use SDS to create the bilayer to stabilize the nanoparticle, then I would prefer to have at least close to 5 to 10 times the concentration than that of the 8 millimolar. Right? Minimum I should keep, from my experience, I would prefer to keep the concentration much higher than that of the critical micellar concentration. How that helps to create the bilayer? The reason is now, if I am creating this, it means that I have already micelles in the solution. So I have micelles of SDS in the solution. The presence of micelle in the solution confirms that all interfaces are occupied. Do you agree with this statement? The presence of the micelle beyond this concentration confirms that all interfaces are occupied. Why? You see, the micelles only form when all interfaces, the one over here, other one over here, other one over here, which I am not showing, so they are all occupied. Only then the micelles are going to be created. So it means that if I want to coat the nanoparticle, I must ensure that the solution phase should possess only the micelles, means predominant amount of the micelles, so that that would ensure the occupation or the passivation of all interfaces, including the interface solid liquid interface, that is of the nanoparticle. That is why this is required. But so that was the part related to the colloidal stability. If you ask me, then why we need to understand the different kinds of shapes of the molecule over here, how they are related to the nanoparticle stabilization. They are in fact related to the crystallization of the nanoparticle in the surfactant solution. So I'll explain that, I think tomorrow probably, because we have to deal further. In the second lecture, I'll be dealing with some of the characteristic thermodynamic quantitative properties of the micellar solution. So okay, so I'm going to finish it over here, and in conclusion, surface active molecules, we have already talked about what is the definition of the surface active molecule, head group and the hydrophobic tail modification. Modification means you can increase the tail length, you can have double tails, you can change the head group from monomeric to the dimeric, and then we have talked about the anatomy of the micelle. The anatomy of the micelle helps us to understand that which part of the micelle is polar and which part is non-polar. Thank you so much for your attention. Any question, please?